Hopkins theory.
Okay.
Thank you.
Got it. All right, so I'm going to talk about a causal framework for nonlinear quantum mechanics. And the question to ask is why? Why would someone want to modify quantum mechanics? If you think about it, the way quantum mechanics was even discovered or constructed is that in the 1900s, there were a number of confusing observations about the atomic world. And a group of people, shown over here, got together in a conference and they came up with some rules, right? That's it. The rules, many of these guys themselves didn't agree with each other. Einstein famously didn't even believe the theory was right. So just a bunch of people got together in a conference and made up some rules. So why should we think somehow that these rules are absolutely accurate, that they could never be changed? It's worth questioning this kind of situation. So if you want to modify quantum mechanics, you want to ask, what are the two main postulates of quantum mechanics from which everything else can be built? And I would say there are only two real axioms or postulates of quantum mechanics. The first is that probability is a fundamental description of nature. The second is that the time evolution of the theory is linear. These are the two things on which quantum mechanics is built. The question now is, which of these two things should we actually modify and why? So in my opinion, probability is a fundamental part of the description of nature and one cannot get rid of it. There are several people who have tried to eliminate probability from quantum mechanics and those theories have gone nowhere. And here is why. Here is why the world is probabilistic and you can't get rid of probability. Here are two facts about the world. If you have a finite system, such as an atom, it has a finite set of energies below any given energy level. So if you, for example, take the hydrogen atom, and let's say you pick some random energy and you ask, how many levels does hydrogen have below this random energy that you picked? And the answer is that it is actually a finite number, right? The system has a ground state, for example. The second is a fact about the world that we also have continuous observables and symmetries. Now, I'm going to argue that these two facts of the world are actually in contradiction with a requirement that you may impose on the system and say that every observable of the system is deterministic at all times. Basically, if you have some observable, if you demand every observable of the system to always have well-defined values, I'm going to argue to you that these two facts about the world are in contradiction with this requirement. So here's a simple example. Could an electron in an atom have a well-defined position? So when I was a child, I modeled the atom as a proton with an electron going around the proton in a circle, with the electron having a well-defined position around the proton, right? This is the solar system model of the atom. The question is, why could this not be true? Why does the electron going around the proton in an atom, why could that not be just like the Earth going around the sun, right? This guy could just be going around the proton in a circle where at every point in time, this electron has a well-defined position. Suppose that were to be true, by which I mean the electron going around the proton with a well-defined position for the electron. Suppose that was actually an allowed energy state of the electron in the atom. Then you could apply a rotation, and rotation, of course, is a continuous observable and a symmetry of the theory, which would then take you from this state to another state where the electron has another position around the atom. That is also, because it's a symmetry, this electron also has the same energy as this electron over here. Now, since rotation is a continuous symmetry of the theory, I could apply this rotation and get the electron to be at anywhere on this orbit, in fact, in all the full 3 dimensions. And that basically means that if this was a well-defined energy state of the electron, so would this state, and so would any other state I can get by applying a rotation. And that basically means this system will now have an infinite degeneracy of states, wherein all of these states will have exactly the same energy. So if the electron, in fact, had a well-defined position around the proton in an atom, then by applying a continuous symmetry, I'll end up getting an infinite degeneracy of states, which then violates or contradicts my original requirement that a finite system must in fact have a finite set of energies. Okay. And you can convince yourself that you need this condition to be true, that a finite system must have a finite set of energies in order for you to have things like a sensible thermodynamics in the world. So quantum mechanics really is a compromise. It sacrifices the idea that every observable must always be fully deterministic and known. It sacrifices that requirement in order to preserve finite set of energy states and have continuous symmetries in observables, essentially by sacrificing determinism and embracing probability. So if you want to get rid of probability in quantum mechanics, you have to fight these two facts, and I don't think you'll be able to do that successfully. Now, if you look at a variety of results that people have proven over the years that show that the world is fundamentally quantum mechanical, such as the Bell inequalities, the Koch-Specker theorems, the SSE theorems, there are a variety of these theorems. All of them are basically based upon playing these games. So for example, if you look at the Bell inequalities, the Bell inequalities are based upon looking at a small number of angular momentum states of the atom. Now, the point is, in an atom, you only have a finite number of angular momentum states, right? They're energy eigenstates of the system. But one can, of course, measure rotation, the angle in a variety of directions, because rotation is a continuous symmetry of the theory. And so what the Bell inequalities ultimately show is that if you are trying to use this continuous observable, namely angle, on a finite set of angular momentum states, you cannot actually have all of the components of the angular momentum being well-defined at all times, simply because a finite number of states cannot possibly represent the answer to every possible measurement you could make for a continuous observable. So that's really what all of these things are based on. So in my opinion, if you're trying to come up with a theory to get rid of probability, you're just wasting your time. What about linearity? Linearity in quantum mechanics is the simple idea that the wave function does not interact with itself, right? So let me give you a concrete example of what linearity in quantum mechanics actually means. And that is the degeneracies of the hydrogen atom. So for example, if you look at the 2s and 2p levels of hydrogen, they're exactly degenerate. This degeneracy is only broken by the Lamb shift to QED. What does that mean? So the 2s level is some spherically symmetric orbit that the electron has around the proton. The 2p is this dumbbell shape. Now, if you naively thought of the electron cloud around the proton as some kind of a charge density, as a classical charge density, you would have naively expected this classical charge density to interact with itself, right? We've all done these problems in classical physics, where you take a sphere of charge and you ask, well, the fact that the charge can interact with itself, how much does that actually contribute to the energy of the sphere? So naively, if the electron cloud was interacting with itself, you may have expected that there would be a contribution to the energy of the atom, of the hydrogen atom, that depends upon its shape. So the 2s and 2p levels, since they have very different shapes, in general, you might have expected the degeneracy between 2s and 2p to be lifted by the electromagnetic interaction of the electron with itself. Yet, that does not actually happen, which is why the Lamb shift is a leading order thing that one goes and measures, which really is a QED effect that has to do with the interaction of the proton with the electron. But there is no fundamental reason why the shape of the electron cloud should somehow be something that one could never detect in a quantum system. In fact, if I put a second electron near the first electron, the second electron clearly is aware of the shape of the electron cloud. So for example, in the 2s versus the 2p level, the 2s guy, the electron cloud will be, the nuclear charge will be much more shielded in the case of the 2s state than the 2p state. The 2p state, there will be some dipole distribution. And so clearly the electron, the second electron will see a very different electric field from this proton than the first electron, okay? So the shape of the electron cloud somehow does not seem to be a protected quantity. So you might in fact think perhaps it is reasonable to see if the electron can see itself. So clearly the fact that a second electron can see the first electron, that seems totally okay. So why can't the electron see its own electron cloud? So why haven't people written down these theories before? And the generic answer is that not very many people have even tried to work on nonlinear quantum mechanics. And the theories that some people have written down have had problems with causality. So I will tell you how to deal with causality in just a second, and why that's an issue even. And then we will talk about how to incorporate ideas about things like measurement in such a nonlinear theory. And ultimately, of course, our world is described by quantum field theory. So we have to basically ask, how does a nonlinearity actually fit into the framework of quantum field theory? So let me address causality from the very beginning. Why is causality a potential issue? So here I've written down a trial Schrodinger equation. I d psi dt is h psi. So this is the usual linear Schrodinger Hamiltonian that you're all used to. And then I've added some terms saying psi squared plus psi star squared. This is my nonlinear term multiplying the wave function psi. So if all I had was just a single particle wave function, this is a perfectly reasonable theory. I mean, you can put in some wave function psi and then can do perturbation theory to compute what these corrections would look like. Okay, so for a single particle theory, there's nothing weird about putting these kinds of terms. It's perfectly reasonable to do so. The question, of course, is that in quantum mechanics, we have to be, first of all, be able to describe more than one particle. We have to describe multi-particle systems. And when you have a multi-particle system, it is in fact the case that you have to be able to deal with entanglement and entangled states. What I'm going to argue to you now is that if you have such entangled states, so what we now have is basically a wave function of two particles, x and y. The x particle is this wave function alpha I, and the y particle is this wave function beta j, and they're now in some entangled state between these two things. What I'm going to argue to you is that if you actually have these kinds of entangled states in the theory, and you put in some wave function like this, right? Some term like this, some psi squared plus psi star squared, these kinds of terms can in fact give rise to a causal behavior, okay, that they violate causality. Let us see how. So here is the main idea. Suppose I take two particles. One particle is with me here on the Earth, the other particle. So I take two particles on planet Earth, I bring them together, I create this entangled state. And then I keep one particle on Earth and I take the other particle and go all the way to planet Mars. Okay. Now, say the particle on the Earth is X and the particle in Mars is Y. What we are now going to do is I'm going to take the particle in X and I'm going to do something to it. I'm going to make it interact with some other environment or apply some operation on it. So generically, when I'm messing with the particle that I have on the Earth, what I'm doing is I'm applying some unitary operation on the particle at X, just at the linear level. Now, when you apply such a unitary transformation on the point at on the particle that you have at planet Earth, what that will do is that it will take the coefficients alpha I of X into some unitary linear transformation. So all the alpha I of X will go to some U, but U is some unitary operator times alpha I of X. What we don't want is that if I change something on planet Earth, I don't want that to immediately affect what is going on in Mars. Now, notice that actually happens in this case, because in this particular theory, the way I wrote it down, I've got these terms psi squared and psi star squared, which now means that if I apply a unitary operation on planet Earth, immediately these coefficients will change. And when these coefficients alpha I of X change, they actually change the coefficients of beta j, right? Because this is some alpha I times beta j, and I've got these terms like psi squared over here. So the moment I actually change alpha I of X, the time evolution of the state Y will immediately change because these coefficients are instantly changing. And the moment that happens, I have therefore affected the time evolution of the particle in Mars instantly, and that is therefore a causal behavior. Okay, so if you don't include nonlinearity carefully, you can end up creating a causal behavior. But it's not like nonlinearity fundamentally has to always lead to a causal behavior. We're, of course, aware of plenty of examples of causal nonlinear theories in classical physics. And in classical physics, the way causality is always enforced is via a Green's function. So if you take two particles and you wiggle one particle and you ask, how does it affect the second particle? The way the first particle affects the second particle is that there is a propagator. There's a Green's function that goes from the first particle to the second particle, and that Green's function is causal. And therefore, it is the causality of the Green's function that ultimately makes sure that we can write sensible causal nonlinear theories of classical physics. So why can't we do the same thing in quantum mechanics? That's the question. And here comes an important point. which is that linear quantum mechanics is actually basis independent. Because the theory is actually is linear, I can choose any basis in order to describe linear quantum mechanics. Even though that is a nice feature of linear quantum mechanics, there is actually a fundamental fact about the world that breaks that basis independence, which is a statement that if you think about interactions in the world are local. They prefer a position basis, right? So when I look at the world, I see you guys sitting at particular locations in space, as opposed to seeing you distributed all over this place in momentum space. And that is simply because of the fact that I'm using light to observe you, and the interactions of light to your atoms in your body are all local. They care about X. So even though linear quantum mechanics is basis independent, a fundamental fact about the world is that the world is in fact local, which means the position basis is more preferred as a way to think about quantum interactions than some general basis independent story about linear quantum mechanics. So I'm going to try and formulate nonlinear quantum mechanics explicitly in the position basis. The reason why this is also important is because the most natural way to formulate field theory itself is in position basis. And if you think about it, problems with multi-particle states are very nicely handled in field theory. And as a matter of fact, that's why we invented field theory. So given that the problems of nonlinear quantum mechanics seem to be tied with causality, and causality is all about position, it would seem to make sense to construct these nonlinearities directly using field theory, right? So this is a kind of a different approach that we are taking than what we normally do. Normally, the way we view field theory is that we think about quantum mechanics as some top-level structure, and we think about field theory as an application of quantum mechanical principles to relativistic systems, and sometimes even in condensed matter systems. So we always think about field theory as being derived in some sense from some quantum principle. I'm not going to do that. I'm going to take field theory and make that as the fundamental way to look at the world. And indeed, that's a perfectly reasonable thing to do, because at the end of the day, all I'm really interested in doing is describing the evolution of particles, and particles are, of course, quantum fields. So this is the framework for the rest of my talk. I'm going to start by giving you the framework of how to actually incorporate nonlinearity in field theory directly. We will then talk about how that implies a single particle Schrodinger equation to understand how single particles evolve. We will then talk about causality, and then we will talk about measurement as well in this particular theory. Nonlinear quantum mechanics turns out to have some extremely interesting macroscopic effects. And these are likely to shock you if you haven't thought about quantum mechanics in a deep way. We will then talk about constraints and tests of these nonlinear quantum mechanical theories that we have managed to get off the ground now. And unlike linear quantum mechanics, it also turns out that nonlinear quantum mechanics has some tremendous cosmological sensitivities. And we will talk about that as well. And then I'll conclude. So let me tell you about the framework. As I said, we're going to directly talk about nonlinear quantum mechanics in field theory. So I'm going to use what is called the Schrodinger picture of quantum field theory. And if you're not familiar with it, let me just quickly tell you what the whole story is. In the Schrodinger picture of quantum field theory, what you do is that you're trying to time evolve some quantum state of fields. So if you take a quantum field, that quantum field has creation and annihilation operators. With that, you can use that to create various single particle or multi-particle states. They're called the various Fock states of the theory. So there is a vector, chi of t, is just some vector in Hilbert space. And that vector has been created by using the creation and annihilation operators of the quantum fields. And you've used those to create some complicated state of the quantum field. Okay, so this is just a vector in Hilbert space. If you haven't thought about it very much, that's all you need to know. It's a vector in Hilbert space. And then we have the quantum fields themselves. They're basically time-independent operators. So basically at every point x in space, there is a quantum field phi. And you can think about the quantum field simply as an operator, as a matrix at every point x in space. Given these operators phi of x, I can construct a Hamiltonian, which is an integral of a Hamiltonian density. Okay, so essentially the idea is that there's a Hamiltonian. The Hamiltonian is a sum of individual Hamiltonian operators at every point in space, where those Hamiltonian operators are in fact constructed using the field operators and their conjugate momentum. And even in quantum field theory, even in relativistic quantum field theory, all we are ever doing is solving the Schrodinger equation. We are saying the quantum state chi evolves as I d chi dt equal to h chi, but h is in fact the Hamiltonian constructed from these field operators. So of course, the Hamiltonian is a little different from non-relativistic quantum mechanics, but that's where field theory comes in. But you're still just solving the Schrodinger equation. Now let me do something a little bit unusual that we normally don't do in regular linear quantum field theory, which is that I'm going to derive this Schrodinger equation itself from an action. Now, this is not the usual action of linear quantum field theory that you're used to. It is not that action. This is just a dummy action that I'm creating. You never use this in regular quantum mechanics because it doesn't give rise to anything interesting. But in my case, it will in fact lead to a simple way for me to incorporate non-linearities, which is why I'm doing it. So here is the claim. You can verify this yourself. Let us think about a quantum state chi. And I'm asking, I would like to evolve a quantum state chi from some initial value chi1 to some final value chi2. Notice that we know the answer to that is the Schrodinger equation. And notice that this Schrodinger equation can be obtained by demanding that this action that I've written down here, okay, by demanding that the correct path that the particle takes, that the state takes to go from one quantum state to another quantum state, minimizes this particular action in Hilbert space. So what we're saying is that chi is a vector. So this chi dot is just a number. And I'm taking the expectation value of the Hamiltonian operator in the state chi. So if you minimize this action, you will gives rise to the Schrodinger equation. And thus you say, oh, the correct quantum evolution of the system is obtained by minimizing this action in Hilbert space. This is completely useless in linear quantum field theory, but it will be helpful for me to incorporate non-linearity. So let us now see how the Yukawa theory fits in this framework. In the Yukawa theory, I'm simply adding a Yukawa coupling, so Y, and then there is some scalar field phi, and there are operators psi bar and psi for the fermions. What does this action look like? Well, I've got my term chi dot minus chi h chi, and all I'm going to do is put in this particular term into the Hamiltonian. So the Hamiltonian now contains Y Yukawa coupling phi of x psi bar psi. Okay, with the chi of t expectation value sitting outside. This is integral over x. This is a time thing. I can move that inside. So that becomes an integral d cube x y chi phi of x psi bar psi chi. So all that's actually happening here is that these are three matrices, three operators whose products I'm taking at the same point x, and then I'm taking the expectation value on the state chi. So essentially all we are doing is basically simple matrix multiplication. This chi is a column. This chi is a row, and this is just a matrix. And I've taken an inner product which now gives me a number. That's it. Now, in the last 100 years of quantum field theory, what we have happily done is that we have taken these operators and we've added many, many nonlinear operators in this particular story. So for example, we take the Yukawa coupling phi psi bar psi. That's one very sensible theory to study. And then we have added higher dimension operators, phi square over lambda, psi bar psi, and so on and so forth. And obviously, we have studied these theories to death. And of course, everybody agrees that this is a very sensible thing to do. These are, of course, non-linearities in the operators, but they're linear in the state. The state only appears here and here. It doesn't appear anywhere inside. Now we can see how to introduce non-linearities in quantum field theory directly, which is that let me take the original action that I saw. And what did we see? We basically have the structure that I've got a phi of x psi bar psi. That's a matrix. And then I have this expectation value of chi that I'm putting in there. The only real rule for this particular action is that this action must be a number. And notice that I have more than one way of introducing a number in this particular story, because if I give myself these products of these three matrices with this chi sitting up here, I can now introduce another number in the story, for example, by looking at this operator and putting a new term, epsilon times chi phi of x chi psi bar psi chi. So this is again a number, right? There's an expectation value. There's another expectation value. So there's again a matrix, a row, a column, and a row that gives me a number. And this is also a number. So by simply putting in various expectation values of chi in this, by taking this operator, I've now gotten myself a situation where if I now perform the Euler-Lagrange procedure to get my equation of motion, I will now find that the Hamiltonian that I've obtained depends upon chi itself, and thus I've now introduced nonlinear terms in the evolution itself. So not just nonlinearities in the operators, but actually nonlinearities in the state itself. And this structure, as you can see, it obeys all the standard rules that one may care about from an action. So I see no particular logical reason not to include such terms. So what we are now going to do is to understand this theory perturbatively in the parameter epsilon. So let's just think about what this does for the Yukawa theory, where we are saying there is some particle phi, and I want to understand how some fermion psi reacts to this nonlinearity. So if you think about what I did, I had my usual Yukawa theory, y phi psi bar psi. And now what really happened is that I put in addition to the usual y phi term, I also ended up putting in this expectation value of the phi field in front of the psi bar psi operator. That's actually what happened in that story. And now you can use that to get the Schrodinger equation that you want to use to time evolve the system. And basically, all that's happening is that this Hamiltonian now contains not just y phi psi bar psi like it used to, but it also now contains this extra piece. How do we think about this theory perturbatively? Well, at zeroth order, when epsilon is 0, this is, of course, just standard quantum field theory. So if I'm giving you a set of psi particles, some fermion psi, I'll just go and do regular quantum field theory and use regular quantum field theory to compute the quantum state of the phi particle. That's just what we do in normal standard quantum field theory. To compute the first order correction in perturbation theory, I can simply use the fact that I've been able to compute the quantum state of the phi particle, or otherwise the chi states, at using linear quantum field theory. And then I'm going to substitute for that zeroth order solution over here, which then tells me how the first order correction appears now, right? Because the first order correction to the wave function, to the state, is going to be given by the zeroth order computation of chi phi chi. And that, of course, just happens in regular quantum field theory, linear quantum field theory. The way this now enters the first order correction is that chi phi chi is not some operator. This is just some classical background field, right? There are no operators living there anymore because I've now taken a expectation value. So this is just a background classical field. So essentially, to compute the first order correction, all we are going to be doing is performing standard quantum field theory on this background field in order to compute the first order correction. Okay. And this, of course, applies to all orders. To compute something to the nth order, I just require the term to the n-1th order, which I'm able to calculate using this perturbative procedure. And the way these n-1 terms contribute to the nth order is simply via a background classical field, which is something that we know to do very, very well. We can immediately see why this theory is causal, because of the fact that if you think about how this nonlinearity is entering into this theory, it enters via this expectation value. So at zeroth order, this expectation value of the quantum field phi is, of course, an observable of regular quantum field theory. And because it is an observable of regular quantum field theory will make sure that the zeroth order term is always causal. And because the zeroth order term is always causal, if you now think about how my first order correction is being computed, the first order correction is being computed from the zeroth order term, and the zeroth order term is now evolving causally. And because the zeroth order term evolves causally, the first order term will also evolve causally. And then you can substitute that to get the second order term and so on and so forth. And you can therefore show, in fact, that this theory evolves causally to all orders in perturbation theory. Let's now ask how this actually affects the single particle state. Okay, it's something that we wanted to do. So we want to say, suppose we have a single psi particle, a single fermion psi. How does its wave function evolve? Because of the fact that the single psi particle is interacting with a phi scalar field. So we will simply compute the expectation value of chi phi chi in the quantum state of the psi field. We know how to do that. At zeroth order, the particle psi will just simply source a phi field, and we can now compute the expectation value in that quantum state. And this is pretty easy to do, because basically what we'll now say is that, oh, the expectation value chi phi chi is simply some charge density of the psi particle, some psi star psi, and evaluate it at where the charge density actually is. And if you want to know the expectation value of phi at some point x because of this, you go and calculate this, and you will find there's a Green's function that automatically shows up in the computation of chi phi chi from just regular quantum field theory. And that, of course, is the usual causal Green's function. And that means, as you expect, everything should actually work sensibly, because indeed, causality is built into this theory automatically from this Green's function. So let's now look at how the single particle equation actually behaves, because now we've computed chi phi chi. Chi phi chi is simply the integral psi star psi times this Green's function. And notice something very important here, which is that the single particle equation I derived, I got it from the field theory itself. And thus the single particle equation that I'm getting here depends upon which field theory I started off with to introduce a non-linearity. So for example, the Yukawa theory gives me a term of this kind, while the 5-4 theory would give me something very different. So the nonlinear terms can take a different character for the single particle theory, depending upon what nonlinear theory they come from, what quantum field theory they come from. So in fact, if you take this particular theory and let's say you compute the Lamb shift, by which I mean, let me have a psi particle go around a proton, for example, and let me talk about the difference in the energy levels between the 2s and 2p states. In this particular theory, you will in fact find that the degeneracy is lifted, because indeed there is now this extra term sitting in here, and this extra term is a self-interaction of the cloud with itself. And because this is a spherically symmetric shape and this is a dumbbell, these two things will in fact be different. And you can show other things in this particular theory, such as the fact that if you actually look at these terms, the way we've introduced them, everything is Hermitian. And so you can actually show that the theory has a conserved norm, and you're able to maintain the probabilistic interpretation of quantum mechanics and things of that kind. And things of that kind. So everything actually works. Let me look at how entangled systems actually operate in this story, which is what we were thinking about earlier. And if you think about entangled systems, let's ignore the algebra that I've written down there for a second, and let's understand the physics. So let me take two particles. Okay, I have a particle on Earth, and I take another particle also on the Earth. I entangle them, and I stick with one particle on the Earth, and I take the other particle and go all the way to Mars. What I'm going to now do is I'm going to actually perform some local operation on the particle that I have on the Earth, and I'm going to ask, how does that actually affect the evolution of the particle all the way at Mars? The way the particle on Earth affects the particle in Mars is not directly. It actually affects it through the expectation value of this phi field, right? That's basically how the nonlinearity is entering in. So what we are now saying is that, let's say I take and I do some operation on the particle at the point X, right? So let me say I shake it. If I shake it, the way I will affect the particle in Mars, the particle at Y, is for the phi field to physically propagate from here all the way to Mars, because that's how the expectation value actually evolves via these Green's functions. And because it's evolving via these Green's functions, automatically it is the case that when I shake something on the Earth, it can only causally impact the evolution of the guy all the way in Mars. Okay. And for those of you who know some of the history of nonlinear quantum mechanics, you might in fact remember that Joe Polchinski showed that in fact nonlinear quantum mechanics was possible. It just needed to have a certain additive structure of this kind. Okay, he didn't quite get all the way down to Green's functions, but he had some additive structure that he was thinking about. And what we find basically is that the structure that Polchinski demanded is an automatic consequence of field theory. Let me also talk about measurement in this particular story. And here is an extremely important part of the story. Many people in my experience in talking about these things have not understood measurement properly in quantum mechanics. Measurement in quantum mechanics is not some mysterious process. Measurement is simply the interaction between a quantum state and a measuring device. So for example, I can take a spin and I bring that spin in contact with some measuring device. Both of these are, of course, quantum systems. They're interacting with each other via some Hamiltonian. So you can simply use a Schrodinger equation to time evolve this state with this state. And if you pick whatever interaction you pick, you can then, the Schrodinger equation will predict that this system will evolve to this complicated entangled state where the spin, for example, goes up and the dial here went to the left, plus beta times the spin going down and the dial moves to the right. This is a prediction of quantum mechanics. It is not some kind of interpretation. It gets a stupid name called the many worlds interpretation, but in fact, this is what quantum mechanics predicts. as long as you admit that this is a quantum system and this is also a quantum system and that the system obeys the rules of quantum mechanics. And all you're actually doing is just bringing these two things into contact and allowing a time evolution. When you do a time evolution, the quantum mechanics will predict that you end up getting this complicated entangled state. When you get this complicated entangled state, because of the fact that this system, the measuring device, is very rapidly entangled with some complicated environmental degrees of freedom, if you're only going to focus on the physics of this spin, which is your simple quantum system, you then typically trace over the degrees of freedom that correspond to the environment and the macroscopic system, because you're unable to do much to that entangled state. And then you can basically just simply think of the subsequent physics of the system as being described by the reduced density matrix of just the spin itself, which you can interpret essentially as a direct sum of worlds. So this is basically where there's a stupid term called the collapse of the wave function that people often talk about, which is simply the phenomenology that when I take this complicated entangled state and I trace over the degrees of freedom of the environment, effectively the system, you can say, quote unquote, has collapsed. But that's not actually true. The full quantum state exists in this superposition. It is just that the subsystem you're describing is described more simply than the full complicated system itself. So we're going to use exactly the same idea to also describe measurement in nonlinear quantum mechanics. I'm not going to do anything different. I'm simply going to say that I'm going to take this quantum system, bring that in contact with my measuring device, and just simply use the Schrodinger equation, this nonlinear Schrodinger equation, now to do the time evolution. The time evolution will, of course, give rise to some complicated superposition of multiple states. There's an important difference between linear quantum mechanics and nonlinear quantum mechanics, because in linear quantum mechanics, in order to create a good measuring device, and by good measuring device, what I mean is that when I create this entangled state, I want this state of the dial, where the dial is to the left, and this state of the dial, where the dial is to the right, to be orthogonal quantum mechanical states. Because that's how you end up with a very nice measurement where you say spin is up, the system is totally different than when the spin is down. That's a good measuring device. In linear quantum mechanics, you can design such a nice measuring device, because to design such a nice measuring device, all you need to know is basically the eigenstates, sorry, the basis vectors of the spin you're trying to measure, and the basis vectors of the quantum measuring device itself. As long as you know those basis vectors in linear quantum mechanics, you can create a designer Hamiltonian that will give rise to whatever specific measuring device you want to have. But in nonlinear quantum mechanics, the whole point is that you want to use a measuring device to understand some unknown quantum state. Now, the problem is, because the quantum state itself is going to take part in your Hamiltonian evolution, because it is now nonlinear evolution, since you don't know the initial state, you cannot automatically pick basis vectors that will guarantee that this state will time evolve into the superposition where the AI and the AJ are orthogonal to each other. So in other words, I can't guarantee that the time evolution will always give rise to spin up going to the dial going to the left, plus spin down going to the dial going to the right, with these two guys being orthogonal to each other, because to some extent there will always be pollution with the state talking to itself and changing something a little bit. So in general, you'll end up getting a little bit of a mixture of what you wanted with things that you don't want. Okay, so I call that essentially an intrinsic source of noise in this kind of measurement. So far, our discussion has been with regular quantum, which is the Yukawa coupling, but you can use these same ideas and also extend these to gauge theories like electromagnetism and gravitation, where simply speaking, these are more easily described in the path integral. And all we're going to be doing is essentially introducing these terms in the path integral, where this is now a state-dependent background field that I've computed using my 0th order path integral, that's regular quantum field theory. And I take the regular quantum field theory, I compute the expectation value in the state, and I substitute that simply to compute the next order in path integral, the first order correction, by putting these in as background classical fields. The same idea also extends to gravitation, where I can put expectation values as a metric in the path integral and use that to describe the time evolution of the system. So with that, let me pause for a second and see if there are any questions before we switch and talk about macroscopic effects of this theory. I've already talked quite a bit, so I may be a little bit late, or I may go a little bit over time, but hopefully not too much over. So I want to ask if there are any questions at this point. All right? I guess not. So let me go and talk about macroscopic effects of these theories. Was there a question or no?
Can I just, sorry.
Yeah, sure.
So in your approach, can you deal with some indefinite number of particles or?
Yes, yes.
But that is somehow the shortcoming of the quantum mechanics, right? So the
I mean, by indefinite, look, you can handle any quantum state you want. So basically, if I mean, because essentially I'm just doing field theory, right? And field theory, I'm allowed to think about an arbitrary number of particles.
That's true.
And this chi that I actually have is the quantum state of the full field theory. So it is just the state that you're putting in with your creation and annihilation operators. And so, yes, that chi contains arbitrary number of particles. It can contain arbitrary number of particles. Pardon?
So the collectively, it includes all possible choices.
Well, it includes all possible initial states. I mean, well, to some extent, right, you have to give me an initial quantum state to time evolve. So, but once you give it, I can time evolve it for you.
Okay.
All right. So let's now talk about some of the truly, I would say, crazy effects of this theory. And these effects will sound wild if you haven't thought about these things. And in fact, I would point out that the wild things that you're going to hear me talk about now, they don't really even come from my theory. They really just come from linear quantum mechanics. They really come from the fact that quantum mechanics fundamentally requires this many worlds point of view that we just talked about. And all I'm doing literally is just following the mathematical consequences of the terms that I've added, right? So I gave you a very sensible looking action from which I derived these evolution equations. And I'm just simply asking, if I obey the standard rules of quantum mechanics in computing these things, what are the mathematical consequences of those terms? That's all I'm doing. So let's look at a simple experiment. Suppose I take a spin and I orient the spin along the x-axis. And I have an experimentalist and I have a laser with 2 photodetectors. So the initial state of this particular theory now contains a spin along x. It contains the quantum state of the experimentalist. The experimentalist is doing whatever. And then I have a laser and 2 photodetectors. So this entire state, because I'm doing field theory, is described by this chi of 0. That is the quantum state of the theory at time t equal to 0. My goal is to create a macroscopic superposition. I'm not trying to create a quantum coherent macroscopic superposition. That's extremely hard. I'm just simply trying to create a macroscopic superposition. And this is very easy to do because all you have to do is measure spin along the y direction. And by measuring the spin along the y direction and depending upon the outcome, I'm going to send this laser along different directions. So here is what I'm going to do. I'm going to measure spin along x. Sorry, I start with the spin along x, measure the spin along y. If I get spin up, I'm going to send the laser to the top. If I get spin down, I'm going to send the laser to the right. Okay. Now, the crucial point is that if you think about the full quantum state of this theory, I took a spin, I measured it, and depending upon the measurement outcome, I did 2 different things. Now, quantum mechanics, linear quantum mechanics predicts using Schrodinger equation that the full quantum state of the theory after I did this measurement is this linear combination where the spin was measured to be up, the laser went to the top, and I got entangled with some environmental degrees of freedom at the top. Spin was down, the laser went to the right, and the environment got entangled with whatever was happening to the right. There is no collapse of the wave function. Okay, the collapse of the wave function never makes any sense. It is just an approximate phenomenological thing that we use because if you're only interested in the spin being up or the spin being down and just the spin and sort of nothing else, because of the entanglement of the environment, we can ignore the other part of the wave function if you're just doing linear quantum mechanics. Okay, but quantum mechanics, in fact, predicts that this is the actual full state of the theory after I make this measurement. That's a prediction of quantum mechanics. If you don't believe it, you don't believe in quantum mechanics. Now we can ask in linear quantum mechanics, if I create this complicated entangled state, which of these photodetectors will light up? We all know the answer to this. Formally, what we are doing is that there's an electromagnetic operator A mu. It couples to current to electrons to the coupling A mu psi bar gamma mu psi. And to figure out whether this guy is lighting up or this guy is lighting up, I compute some transition matrix element, right, to compute my excitation state or whatever. And so what you know, of course, is that when in this part of the wave function where the spin went up, the laser went to the top, if I compute the electromagnetic field A mu at the point at the right on the specific state T where the laser went to the top, this guy is 0. And because this guy is 0, this electron here does not get excited. And that's why this photodetector is called. I'm not telling you anything fancy. But notice something very important. Okay. If I compute the expectation value of chi, of A mu in the state chi, the expectation value of chi, A mu chi, right? Whether you're at the top or at the bottom, this expectation value is non-zero. This is very important because the full quantum state is this thing plus this thing. So when I take the expectation value of A mu both at the top and at the right is just a non-zero number. The reason why it's a non-zero number is because, for example, if I'm going to this part, if I'm simply computing A mu of xt, right, I get two contributions. I get a contribution from this part of the wave function, which of course is 0, but now I get a contribution from this part of the wave function, and that is non-zero. And because the contribution from this part of the wave function is non-zero over here, I find that A mu of, let's say, xr, that expectation value is non-zero, irrespective of what the environmental degrees of freedom are doing. That's extremely important. So in nonlinear quantum mechanics, what I'm now doing is basically that I have my usual term, but I've also added this expectation value term. That is my state-dependent nonlinear term that has entered into my equations, that are now entering into how the electron is now going to behave. And because these expectation values are non-zero in both these cases, what you will now find is that in this part of the wave function where the electron went up, the laser went to the top, this photodetector got hot, you're going to find at order epsilon, because the expectation value is non-zero, at order epsilon, this photodetector also lights up. And in the other world, the other arm, this guy, of course, lights up in linear quantum mechanics, but in nonlinear quantum mechanics, or at order epsilon, this guy will also light up. So effectively, what is happening, right, is that I created this complicated superposition where, to use the colloquial terms, there are two worlds that we have created. Spin went up, laser went to the top, that is one world. Spin went down, laser went to the right, that is the second world. In linear quantum mechanics, these two worlds cannot talk to each other because the wave function doesn't talk to each other. But now in nonlinear quantum mechanics, I have allowed the two parts of the wave function to talk to each other. And because they're talking to each other, you get this extremely strange result, strange sounding phenomenon, that the laser that went to this part of the wave function is now affecting what's going on over here. This, of course, is extremely strange and weird, but I don't see anything here that is logically wrong. It's just weird. That's all. Okay. So that is the biggest sort of macroscopic effect of nonlinear quantum mechanics. That is very, very crazy sounding. But the crazy sounding stuff really just comes from linear quantum mechanics, and that in linear quantum mechanics, by creating a macroscopic superposition, I've in fact created these many worlds, if you like. So let us now talk about constraints and tests on this scenario. I began this whole discussion by talking about the Lamb shift. So let's ask, how well have measurements of the Lamb shift constrained this kind of theory? So the following is in fact true. If I take a proton and I fix the proton at a well-defined position, I nail the proton to a point, and suppose I look at the 2s and 2p levels of hydrogen, I'll in fact find that the 2s and 2p levels of hydrogen, because they have different charge distributions, there will be a contribution to their energy level, that to their self energy, that depends upon epsilon, because of which the 2s and 2p levels will in fact have a level splitting, right? So you might naively think that if I look at the Lamb shift has been evaluated to 13 digits or 14 digits. So you might naively think this epsilon parameter should be tested at least already from linear quantum mechanics, from the Lamb shift to 13 digits. This turns out to be completely false. And it is because of a very, very fundamental point about nonlinear quantum mechanics. In linear quantum mechanics, when we are trying to understand the energy of the hydrogen atom, what we always do is we go to the center of mass coordinates, right? We say, let me go to the center of mass coordinates. The center of mass coordinates, I can decouple the motion of the center of mass from the relative coordinates. And when we're trying to solve for the energy levels of hydrogen, we're only always solving for the relative coordinate, right? The center of mass coordinate we completely ignored. This has an important consequence, which is that if you take the hydrogen atom, and let us say you spread its center of mass wave function to, let's say, a trap of size 1 micron, that is one system. Or you take the same hydrogen atom and you spread its center of mass wave function to the size of the galaxy, which of course you can do in quantum mechanics. In both these states, if you now ask, how much energy do I need to ionize hydrogen? The answer is the same. It is 13.6 eV. Whether the center of mass is spread over 1 micron or spread over the size of the galaxy, the energy of hydrogen is the same in the linear theory, right? Because that's because of the fact that center of mass degrees of freedom don't count. They decouple from the relative motion. And so the energy of the hydrogen atom, the ionization energy, does not care about how much the wave function is spread out. But this is fundamentally not true in nonlinear quantum mechanics. In nonlinear quantum mechanics, I'm actually, if you think about the nonlinear term I've added, I'm actually looking at the expectation value of the electromagnetic field. So if I take the hydrogen atom and I spread it over, let's say, a 1 micron trap versus spreading it out over the size of the galaxy, the expectation value of the electromagnetic field in these two states is now dramatically different. In the case of the galaxy, obviously, it is just one particle now spread over the size of the entire galaxy, which means the expectation of the electromagnetic field is vanishingly small, right? So what you now learn is that the nonlinear effects of quantum mechanics, the nonlinearities, they really care a lot about how localized the wave function actually is in physical space. Now, in all of the lamp shift experiments people have done, they've never bothered to localize the hydrogen atom very well because they don't think about it, because in linear quantum mechanics, you never think about doing it. In fact, if you use neutral hydrogen to perform a measurement of the lamp shift, because all I am sensitive to is the expectation value of the electromagnetic field, in neutral hydrogen, that expectation value is automatically 0. So even though you have in fact thinking that you're probing quantum mechanics to the 13th digit using the lamp shift, because you are using neutral atoms, the limit of the lamp shift on this particular theory is nothing at all. Epsilon could be order 1, and the lamp shift actually is not constraining this theory at all. So this is a very important point, because when we think about our confidence that we have in testing quantum mechanics, most of our confidence in testing quantum mechanics comes from studying atomic and nuclear systems. And that is because atomic and nuclear systems are where we actually first discovered quantum mechanics. So it's very natural for us to go and look at such quantum systems to constrain quantum mechanics. But what we are learning is that unless you actually localize the center of mass very carefully, all of those tests are actually useless in testing nonlinear quantum mechanics, because of the fact that the expectation value is crucially, depends a lot on how spread out the wave function actually is. So the leading constraint on these theories are completely accidental right now. They come from facts like we have managed to trap ions. So when we've trapped ions, right, if the parameter epsilon we put in, let's say, was positive, so the ion is repelling itself, then I take an ion trap and I put an ion in it. Because of the Coulomb repulsion, if epsilon is too big, the ion can sort of get away from the trap. So the fact that we've successfully trapped ions means epsilon is less than 10 to the minus 5 if it is a repulsive interaction. For attractive interactions, this limit doesn't apply, and there isn't really a direct limit in that particular case. We are now in an interesting situation where, although I've told you that the theory is currently ill-constrained, not constrained by existing tests of quantum mechanics, it is in fact relatively easy to test this in a variety of experiments, and these experiments are being currently done. So here are two kinds of experiments currently being done. The first ones, they're going to create a macroscopic superposition of some kind, and then we're going to search for this expectation value of either electromagnetism or gravity by this protocol. So here's an experiment going on in Boston University right now by Alex Sushkov. He's doing a version of this experiment. So you take a spin, let's say along x direction, you measure spin along y. If you get your spin along y, here's what you do. You take a squid and you take a magnetic field. You turn on the magnetic field, let's say between 10 o'clock and 10:10 a.m. if your spin was up. And then you turn off the magnetic field between 10:10 and 10:20. If the spin is down, you turn off the magnetic field from 10 o'clock to 10:10, and you turn it on from 10:10 to 10:20. In linear quantum mechanics, of course, the squid will see a magnetic field between 10 o'clock and 10:10 here. and it'll see a magnetic field between 1010 and 1020 here, and no magnetic field between 1010 and 1020, and no magnetic field between 10 o'clock and 1010. If there is a nonlinear interaction like this, what you will now find is that when the magnetic field is actually off over here, that is between 1010 and 1020, at order epsilon, the fact that you've turned on a magnetic field here will leak in and give rise to a non-zero effect. That is basically what Surjeet is doing at Boston University. You can also do a similar test for gravity, where what you do is, depending on the outcome of the spin, you can take an accelerometer and you can decide to bring a large mass, like a truck or a big block of lead, next to the mass. So what you do is that between 10 o'clock and 1010, let's say you bring the mass close to the accelerometer, and between 1010 and 1020, you take the accelerometer, the mass away from the accelerometer. And in the other world where you got spin down, you do the opposite thing, and then you see if there's an interaction between these two guys. That's basically what my friend Jason Hogan is going to do at Stanford. This is an experiment that's going on at Berkeley by Hartmut Hafner. So what he's going to do is he's going to take an ion, and he's going to split the ion into two parts and make them re-interfere. In linear quantum mechanics, this part of the ion will not interact with this part of the ion via its Coulomb field, because the ion doesn't see itself. But in nonlinear quantum mechanics, this part of the ion will interact with this part of the ion via the Coulomb field. And therefore, you'll end up getting a phase shift in this experiment that depends upon how much of the ion is on which path. And that's an extremely useful thing, because all of your noise sources don't care about that, it turns out. The noise sources only care about other aspects of the system. So this gives rise to an intensity-dependent phase shift in this experiment. Basically, how much of the ion is in which part, and that gives rise to an intensity-dependent Coulomb shift, which is something you can go look for. And that's an experiment going on at UC Berkeley right now. So I'm basically a little bit out of time, but this will only take another 5 minutes. So I beg your patience for this. So let me talk about how, unlike linear quantum mechanics, nonlinear quantum mechanics is extremely sensitive to cosmology in very weird ways. So this will only take about another 5 minutes. Here is the fact. Okay, I've added my nonlinear terms like this. Okay, chi, a mu chi, they're in there. Now remember, in quantum mechanics, I have to be able to describe many worlds that can be in quantum superpositions with each other. So I can take a state of the wave function of the universe, which is alpha times our universe meaning where I'm sitting right now at this point in space and time and talking to you, plus beta times another universe, which is a allowed quantum state, is a superposition with me. Okay, that is allowed by quantum mechanics. And this other universe that I'm talking about, I'm not here, it's just empty space. It's some completely different, bizarre universe. Now, the nonlinear terms are appearing in as expectation values of operators, a mu, taken on these states. So they're basically alpha squared u a mu u plus beta squared m a mu m, but we're simply measuring the expectation value of this operator in the full quantum state. Now comes a very important point. If you think about the fact that when I, for example, do my laser experiment, right, only in the state U, which is our universe where I'm sitting here doing this experiment, is a laser on, the electromagnetic field is on, it's doing all these things, right? So all of that occurs in the state U. When I look at the full expectation value, that expectation value is now alpha squared u a mu u, okay, and beta squared m a mu m. But in this part of the wave function, I'm not there. I'm not turning on the expectation value. I'm not doing anything at all. So let's say I'm an empty space. If I'm an empty space, this expectation value is now simply alpha squared u a mu u. Now comes a very important point, which is that if alpha is small, right? So whoever created the universe, if for whatever reason they made alpha to be 10 to the minus 500 and beta to be nearly 1, then even if epsilon is order 1, by which we mean quantum mechanics is fundamentally nonlinear, even if quantum mechanics is fundamentally nonlinear, whatever effect I can create in the laboratory will always be proportional to alpha squared, okay? And I can never, ever change this value of alpha squared. It just depends upon the initial state of the universe. So if beta is big, I'm completely dominated by this metric, or by this state, which means that all of these laboratory experiments that we talked about will be useless because of the fact that whatever effect I'm looking for is always proportional to alpha squared. And thus the local exploitability of these nonlinear quantum mechanical things are dependent solely a lot on these unchangeable initial conditions. This is a huge difference from linear quantum mechanics, because in linear quantum mechanics to this day, you have never ever pondered ever what the value of alpha and beta are, because you don't care. In linear quantum mechanics, whatever the state of the universe, alpha u plus beta m, whether alpha is nearly 1 or 10 to the minus 500, in linear quantum mechanics, the state u and alpha u, they evolve exactly the same way. That is what linearity means. So in linear quantum mechanics, you never care about the value of alpha, but in nonlinear quantum mechanics, you absolutely care about the value of alpha, because that's what the nonlinearity is. The state depends upon itself. So this is a very bizarre thing where if the universe that we live in, where we are existing right now, is a very small part of the overall wave function of the universe, even if quantum mechanics is fundamentally nonlinear, our ability to discover it gets extremely suppressed. You can ask if one can actually ever boost this effect somehow. So you may try to, for example, take this operator chi a mu chi and divide that by an operator conditioning on our existence, for example. But this can never be done in a local theory, because this operator, this expectation value you're trying to take is an expectation value conditioned on our environment. And the environment is precisely a non-local operator, is a non-local object. So there is no local operator you can ever write down that will project this. Okay, so you can never do this. So this is, I think, a very general feature of nonlinear quantum mechanics. However, not all effects go away. So this is the final thing that I will say, which is that you may then wonder, right? If alpha is fundamentally small, and that is actually a prediction of inflationary cosmology in many ways, if alpha is fundamentally small, is it impossible to discover nonlinear quantum mechanics? Surprisingly, the answer is no, because this all we know is that if you are in this kind of a state like this, right? All I require is some field that needs to have a non-zero wave in the majority of these wave functions that I am in superposition with. And there is one field that always has a non-zero wave, and that is the metric itself, right? Laser fields, all these things will generally be zero. They're in most of the universe, while the metric itself is non-zero. And because the metric is now non-zero, you can now get novel gravitational effects. So for example, if you take the gravitational field of an isolated body, right, like the Schwarzschild metric, that is the metric, because I have matter in my world, that matter is now creating the Schwarzschild geometry. That's what your matter is usually responding to. But in nonlinear quantum mechanics at order epsilon, it now gets this contribution as well. And this extra contribution is the metric in the rest of the universe in the quantum mechanical sense. And that is just some kind of flat space. So what you now see is that the effective geometry seen by your particle is now not the Schwarzschild geometry. It is this sum of these two things, where you basically notice that the nonlinearity enters at the quadratic order in GR. And so this term basically is a second order correction to GR. Okay. So it will show up in strong field tests of general relativity, which we are just now beginning to do with experiments like LIGO and the Event Horizon Telescope. So with that, let me conclude my talk. Sorry for going over time. And the basic point I wanted to get across to you is that quantum field theory can be generalized to include nonlinear state-dependent evolution. I don't see anything logically wrong with what I've said. Very interestingly, conventional tests of quantum mechanics in atomic and nuclear systems, they do not actually probe causal nonlinear quantum mechanics. However, we are in a very interesting situation where straightforward tests, experimental tests, are still possible to probe nonlinear quantum mechanics, and it's actually happening right now. And very, very interestingly, what we have discovered is that these nonlinearities are extremely sensitive to cosmology. And in certain cosmologies, all of these lab tests may give rise to null results simply because this coefficient alpha is extremely small. But it, in fact, does not mean you cannot discover nonlinear quantum mechanics. You kind of just have to do nonlinear quantum mechanics using things like LIGO. Very strange use of LIGO. But essentially what you're trying to look for is that you can look for the metrics of the other universes that you're somehow in a superposition with, interfering with your space-time. So with that, let me conclude, and I'm sorry for going a little bit over time.
Thank you very much for the nice talk. Let's open it up for question and discussion. So any question?
So it's a lot to take in. So, if you're confused about any aspect of the story, I'm happy to spend time, whatever it is, to tell you about it.
I have actually one nice question which I may miss. So when you introduce non-linearity and for example chi-phi chi, then what chi do you use for calculating that part? You just use the, for example, just leading zeroth order, or I mean, so
well, what I'm saying is that, so just think about field theory, right? In field theory, what we will say is that I gave you an initial state of the field. So for example, it could be like 10 particles, okay? So what you did is that you took your creation and annihilation operators of the fields, and you use those, A dagger, whatever, to create 10 particle states, okay? That's your initial chi of t. And then you use the Schrodinger equation to time evolve that system using linear quantum mechanics, right? We're doing it perturbatively. So in linear quantum mechanics, it will now tell you, given the state at time t equal to 0, I can now time evolve the system forward, and I get the state at time t. Once you have the state at time t, you can now take the expectation value of the phi operator, for example, in that state.
Okay, then after that you include that chi-phi chi, then calculate again about that non-linear quantum mechanics.
Yeah, so now exactly. So now you take chi-phi chi. So chi-phi chi, notice, is just a number, right? It's just it's a C number field. It's a background field. There are no operators in it anymore. So you take that, and and you're just doing perturbation theory. So in perturbation theory, in fact, let me share my screen. So it's again, so it's clearer. Let's go back to my slides here. You can see my slide. Let's see, where is this term? Right. Yeah, so what's happening now is that this is sitting in your Hamiltonian, and this is now simply sitting as a background classical field. That's it. So you're just using this background classical field to compute, using perturbation theory, how this guy will respond to this order epsilon perturbation.
So, for example, using this formalism, for example, you calculate some expectation of value of some field, then
yes,
and take the norm, you have some Brian cat, and that Brian cat is not directly related to this kind.
Right, good. So yeah, so in perturbation theory, this would be chi naught, that is a 0th order chi, right? So once you got chi naught, you would substitute that in here, and then you do perturbation theory to compute chi 1. Chi 1 is the first order correction to the state. So now you've got your state as chi naught plus epsilon chi 1. Now that you've got chi naught plus epsilon chi 1, to compute the second order correction, you would now, since you already computed chi 1, you can now compute this state, which would now be chi naught plus epsilon chi 1 phi chi naught plus epsilon chi 1. You see, and that'll give you tell you how to compute the second order correction and so on.
I see.
Yeah, so you're just doing perturbation theory, like nothing complicated.
Yeah, I mean, I thought maybe it's similar to kind of Schwinger-Keldysh formalism or Indian formalism in cosmology, or non-linear. No.
Yeah, there are, here's a simple way to understand why what I'm saying is not going to give rise to logical inconsistencies, because essentially, to some extent, these terms should be similar to, I mean, in fact, all the computations they're doing are similar to like mean field theory, right? So if you think about mean field theory, or, any of these things, we would generally, like, if I had a large number of particles and I want to understand how any one particle is responding to a large number of particles, I can do some kind of mean field approach. And in the mean field approach, we're just simply saying, oh, the whatever, the phi field from a large number of particles is just some background classical field, and let me use this background classical field to compute my corrections, right? So you will, in fact, you probably may have encountered this kind of term before. It is just that in all of those contexts, you're still thinking about the theory fundamentally linearly, right? So the distinction here is that I'm actually putting the full quantum state itself in this, but the calculational apparatus is very similar to what you may have been familiar with in mean field theory.
I see. Any other questions?
Sorry, I need much more time to digest your paper. But when you talk about the multiverse, the other universe, did you mean the multiverse, something like to completely like a non-causal?
No. Good. So yeah, this is a common question. So there is a multiverse of Raphael Bousso and Lenny Susskind, people like that, where the idea is that we are here and I go a long distance in space. Maybe the properties of the space are completely different or whatever because of complicated field theories, things of this kind, right? That is not the multiverse I'm talking about. That is a speculative belief about the kind of vacua that are there in the universe. May not be true. I have no particular objections to that possibility, but that is not what I'm talking about. What I'm talking about is just in quantum mechanics, I should be able to describe a superposition of space-times, right? Quantum mechanics allows you to have superpositions. Gravity is, of course, just a regular quantum field. And just like how I can take two lasers and create a superposed quantum state, I can also take two metrics and create a superposition. Right? So that is just there in quantum mechanics. So it's not even speculative. It's just what quantum mechanics allows you to do. So what I'm saying is this, right? That if you just take that thing that is allowed in regular quantum mechanics, and I'm just simply taking our world to be a tiny part of that superposition. In nonlinear quantum mechanics, the fact that we are a tiny part of the superposition makes it difficult for us to perform certain kinds of experiments to see those nonlinearities. But at the same time, not all hope is lost, because you can kind of see this in these gravity wave detectors, for example, in LIGO or things of that kind.
Okay, thank you. And another question was, so to deal with the non-linearity in quantum mechanics, is it like the introduction of the QFT is a compulsory, is the only option?
I actually think it is necessary because of the fact that, see, the difficulty in nonlinear quantum mechanics has always been causality.
Yes.
Right? And to think about causality, you need to talk about X. And I would say that basically that's actually one of the reasons why I really like our story, is because it's, it's much less ad hoc than it might seem, because in a sense, we are looking at some very sensible field theory ideas and concepts and structure, and sort of just porting it over. So I think if you're trying to come up with a causal theory, it's very hard to formulate a causal theory that does not know about position. And once you have decided to go forward with position as your fundamental basis of looking at the world, field theory is just the natural thing to do.
Okay.
Also, because a lot of the causal issues really arise because of multi-particle states, and field theory is in fact the only sensible way to talk about multi-particle states.
Sure. Yes. Okay. So yeah. And how about so another thing was, so here in field theory, we know like all this RG running when you have a different scale. So here you can do all these things naturally in this formalism as well.
Yeah, I mean, like none of that really changes. I mean, one can talk about, like, in fact, even the nonlinear terms could in principle be running, right? Because all I'm doing perturbatively is just the fact that I've given you a rule for how to introduce a nonlinearity order by order. And at each order, you're just doing standard QFT calculations.
Okay.
So nothing dramatic even happens in this case.
Okay. Okay, thank you.
Sure.
Yeah. I'm done. Yeah.
Any other questions? Actually, I have one more night questions. When you detect the, for example, deviation from the linear quantum mechanics from the experiments, then you can distinguish it is from the non-linearity or some other, for example, unknown effect from kind of classical way to.
Yeah, very good. That's a great question. So the question you're basically asking is, how do I know that I discovered something as crazy as nonlinear quantum mechanics? Maybe I just discovered dark matter or something else, right? Just some change to the Hamiltonian. And there's actually a very nice way of doing it. In fact, this is how our experiments are being run. So what do we do, right? So we have this spin, for example, pointing up or pointing down. And so call that a bit, a qubit, right? Like there's a qubit that if it's 1, I do something. If it's 0, I do something else. Now, the way we run the experiment is basically that there's a computer that is reading these bits from some string, okay? Now, there are 2 ways in which I can give you that the initial string. So what we do is that we randomly either supply the random bits either from a quantum process, by which we mean either from an IBM quantum randomizer, where there's a genuine quantum thing, there's a spin, the spin goes up or down, versus, and also a classical randomizer. So classical randomizer just does something and gives you a classical bit. The important thing is that I get my signals only when I actually literally split the wave function like this and allow the communication, right? So if I gave you the quantum one, anytime I gave you the quantum one, you know that that another world with the 0 was also created, but I was doing the opposite thing. But if I gave you a classical one, there was no classical 0.
Mm-hmm.
So the way we will distinguish this from any kind of new physics is basically, we do a blind test. We basically get a sample of 1s and 0s. We don't know, when we unblind the test, we don't know if we got it from 1 or 0 or whatever, right? We don't know if we got it from a quantum string or a classical string. And then we see the effects. And then let's say we see a positive effect. We would only say the positive effect is due to nonlinear quantum mechanics if it shows up when we do the unblinding. We see that the effect only exists for the quantum splits and not for the classical splits.
I see. So can we also calculate kind of barrier inequality or kind of that thing? I mean, for example, that's crazy. I mean, but when we classically split, but maybe there is some unknown effect, kind of effect of downspin. I'm not sure.
So sorry, you were thinking about a Bell inequality or thinking about, I didn't quite catch what you said. So,
I mean,
some unknown effect.
Inequalities. No, just forget about it.
Yeah, I mean, I don't think we'll change any of the inequality kind of statements because those are really just relying on the fact that there's a finite number of energy levels. So one of the things we showed in our paper is that the non-linearities, if they're weak enough, do not actually change the eigenstate nature of, I mean, one can still have energy eigenstates, perturbatively, everything remains okay. So we will not actually be changing the number of energy eigenstates in the system, and thus things like the Bell inequalities, etc., will still hold.
Okay, thank you very much. Any other questions? If not, let's thank speakers. Thank you very much for the nice talk.
Thank you very much for your invitation. Thank you. Take care.
Okay.